Welcome back to the Deep Dive, the place where we take stacks of complicated source material articles, white papers, and research, and distill them into the most essential, sticky bits of knowledge you need.
Today, we are strapping in for what is, for many, the great unknown, the nuts and bolts of enterprise data analytics. We're moving beyond just hearing buzzwords like big data.
Yeah, that one's everywhere.
Exactly. We're going to actually trace the full architectural journey of information, from the moment a user clicks a button to the second a major business insight lands on a CEO's dashboard.
That's right. And our listener's mission today, your mission, is really tailored for someone taking their first foray into this complex engineering world. Think of this deep dive as your architectural blueprint. We are not just listing tools, we are explaining why certain specialized technological tools are chosen at specific stages in the data lifecycle. We're answering that core question. How does a tiny, insignificant event, like tapping a phone screen, turn into a multi-million-dollar business insight?
And to map this territory, we're following a clear 5-stage roadmap that governs, well, pretty much all data analysis projects. First, you have ingest.
How the data gets in.
Exactly. Second, process, where we clean it up, transform it, enrich it. Third is store, where it's going to live. Fourth, analyze, where we actually extract the meaning.
And finally, display, where humans can actually look at it and make a decision.
That's the one.
So before we even look at that first stage, we have to grasp this core philosophical difference that really it defines the entire field of data engineering. It dictates every single tool choice you'll make later on.
It really does.
We're talking about batch data versus streaming data. This is our most crucial analogy to get our heads around.
Let's start with batch data. This is, the older, more traditional way of handling information. Imagine you live in a town and the local transportation authority decides that instead of running small, individual buses all day, they're going to wait until a fixed time, say 6:00 a.m., gather everyone who needs to travel and load them onto a single, massive, articulated bus.
Ah, okay. I see where this is going.
That's batch processing. You collect large groups of data over a defined period, maybe hourly, maybe daily, and you process them all at once in one single big job.
It's super efficient for those predictable, massive jobs like, I don't know, running payroll or generating a quarterly report. But there's a huge inherent delay built right into the
A
system.
massive delay. You have to wait for the bus to fill up.
Right.
Now, you contrast that with streaming data. And this is the modern requirement. It's driven by constant internet connectivity and real-time interaction. Think of a never-ending conveyor belt, or even better, a steady stream of water flowing through a pipe. As soon as a single click event, a single sensor reading enters the system, it's processed almost instantly.
So the data is live, it's flowing, and it's processed one event after the other. So if batch is a giant file transfer that happens once a night, streaming is an endless Twitter feed. I can see why most modern consumer-facing systems need a mix of both. You need that live feed for instant feedback, but also the nightly job for complex reporting.
You've hit it, exactly.
Yeah.
And because these architectures get so complex, we need dedicated tools. We are going to meet the core heroes that manage these flows in the cloud environment we're studying today.
Okay, who are they?
We've got Cloud PubSub for ingesting these high-speed streams, Cloud Dataflow for transforming and processing data using a unified model, and then the behemoth, BigQuery, for storing and analyzing those massive multi-petabyte data sets.
Okay, let's unpack this data journey starting right at the beginning of the pipe. So ingestion. It's simply how we get the raw material, the clicks, the sensor readings, the transaction records from the source system and reliably into the analytical system.
Right.
It sounds like it should be the easiest part, but when you introduce speed and scale, it becomes the first major engineering hurdle.
Oh, absolutely. Getting data in reliably, especially with those unpredictable streaming flows we just talked about, is a massive architectural challenge. The key difficulty is that the application generating the data, it often produces it way faster than the analysis system can consume it.
Our first hero in this streaming world is Cloud PubSub, which is short for Publish Subscribe. The sources really emphasize its primary function, managing the stream of events and acting as a messenger service that, and this is the key word, decouples data producers from data consumers.
Yes.
We need to drill down into the practical implication of decoupling. What real business problem is this solving?
It solves the problem of back pressure and unpredictable load, which translates directly to massive financial risk.
Okay.
Let's go back to our website example. Let's say on an average day, your e-commerce site generates, 1,000 user click events per second. Your internal analysis system is provisioned to handle that reliably.
Sure, that's business as usual.
But then you get featured on a major news site, or you launch a viral product, and that traffic suddenly bursts to 8,500 clicks per second, according to our source material.
That spike isn't just inconvenient, it's catastrophic. The consumer, the application trying to read and analyze that data would instantly become overwhelmed. It would drop messages. It would likely crash entirely.
Right.
You just lost the data from 7,500 clicks per second, which means lost sales data, lost marketing insights, a broken dashboard. I mean, it's a disaster.
Precisely. PubSub acts as an infinite elastic buffer. The producers, which are the website servers, they can just scream data into PubSub as fast as they possibly can at 8,500 events per second, or even higher.
And PubSub just soaks it all up.
It just queues those messages. The consumers, the analysis systems, they can then read the data at the rate they can safely handle, maybe 1,500 events per second. PubSub holds that backlog until the consumers catch up. This effective decoupling means the producers never stall and the consumers never crash from overload.
It's the ultimate shock absorber.
That's the perfect analogy for it.
So that shock absorption capability sounds like the #1 reason to use it. But the sources also stress its architectural benefit in supporting many-to-many relationships.
Oh, that capability is huge for enterprise scale. Imagine you have multiple sources sending data: a website, a native mobile app, and an internal sales tool. All of them can act as multiple publishers sending data to the same central PubSub topic.
Okay, so one central collection point.
Right. But even more importantly, you can have multiple completely different consumers subscribing to that exact same stream. One consumer might be calculating the live click dashboard. Another might be archiving the raw data to a storage bucket for later machine learning training. And a third could be triggering an alert system if a certain click pattern is detected.
You're essentially turning one fire hose of data into 3 different parallel systems without duplicating the ingestion effort at all.
Exactly. It makes simultaneous, varied consumption possible, which is essential for data democratization. And because sensitive data, like transaction records, might be pushed from internal application server VMs to PubSub, security is paramount right at this entry point.
And our sources guide us on the recommended authentication method for those internal applications.
They do.
The recommended method is pretty straightforward, ensuring the VM's service accounts are granted the appropriate Cloud PubSub IA roles. That seems like a small detail, but it's critical. Why not just use API keys or encrypted passwords?
Because API keys and passwords are secrets that have to be managed, rotated, and secured, and they often live within the application code itself. That creates a massive security surface.
Right, a point of failure.
A huge one. By using IAM roles assigned directly to the computational resource, the VM service account, you follow the principle of least privilege. The underlying platform handles the authentication transparently and securely. The VM itself is the credential, and if the VM is shut down, the credential just disappears.
It keeps the authentication process secure and managed centrally by the cloud provider.
Exactly.
So PubSub is our hero for cloud-native streaming, but not all data starts in the cloud. Many enterprises still rely on legacy, on-premises systems, maybe a massive Oracle transactional database that sits in their own data center.
A very common scenario.
If you desperately need to move the changes happening there in real time into your cloud data warehouse, like BigQuery, to power a live dashboard, how do you handle that?
This is a classic, complicated problem known in the data world as change data capture, or CDC. For decades, this required complex, brittle manual configuration using custom scripts or dedicated third-party software to monitor the source database logs and replicate those changes.
A headache.
A major one.
And the source points us to a specialized, modern tool designed specifically for this exact replication use case. DataStream.
Right. DataStream simplifies this whole process because it's a modern CDC service. It's pitched as a serverless and easy-to-configure solution. The key is that it doesn't just do a massive slow dunk of the entire database.
What does it do then?
It monitors the transactional logs, so the journal of inserts, updates, and deletes of the source database, like Oracle, MySQL, or PostgreSQL, and it streams only the changes straight into the destination, which is often BigQuery or cloud storage.
So that eliminates the massive computational load of constantly reading and moving the whole source database. It's only moving the diff.
Exactly. It simplifies the movement of historical data into a continuous streaming pipeline, letting you instantly populate those live dashboards with data that originated outside of the cloud without running massive, painful batch jobs every few hours.
It addresses that hybrid architecture requirement perfectly.
It does.
Okay, we've established that PubSub is fantastic for throughput and resilience, but we touched on its limitations. Our source material raises a fascinating and critical challenge. What if you have a sensitive legacy streaming backend data API that expects events in strict chronological order with no repeat data?
Right, think financial transactions or complex sequencing data.
Yeah, that's a great example.
This is where the inherent challenges of distributed systems really surface. PubSub is designed for maximum availability and throughput. To achieve that, it makes a trade-off. It guarantees at least once delivery, which means a subscriber might occasionally receive a message more than once.
Oh, that's a problem.
And due to network latency, messages might arrive slightly out of the strict chronological order they were sent.
And for financial data, if a consumer receives a deposit transaction twice or processes a withdrawal before the deposit that preceded it, the entire downstream system breaks. You get inaccurate balances, system failures.
It's chaos. Precisely. So PubSub alone is insufficient for that guaranteed chronological exactly once delivery requirement. We have to immediately transition to the next stage of the data lifecycle to intervene and enforce that data quality.
So we need to introduce our powerful processing hero right at the ingestion point. The architectural solution must be a cloud PubSub to cloud data flow combo.
That's the answer. Data flow is used here specifically to manage the state necessary to enforce these rules. It takes the stream from PubSub and applies complex stateful logic to buffer events, check timestamps, discard duplicates, what we call deduplication, and ensure that only unique, chronologically correct records are outputted.
So it's the gatekeeper.
It is. It's the gatekeeper that guarantees that crucial FIFO, first in, first out delivery model before passing the data downstream.
That makes a lot of sense. It really shows that ingest and process aren't always these distinct, separate stages. Sometimes they have to work together immediately to establish the necessary data quality foundation before the data is even considered in.
You've got it. They're tightly coupled in this case.
We've got the raw data reliably flowing into the system, thanks to PubSub and DataStream. Now we enter the processing stage, the data kitchen, if you will, where we actually turn that chaotic raw material into structured, meaningful, analytical information.
Yeah, this is where you clean it, you transform it, and often you enrich it. Maybe by adding geopolitical data based on an IP address or combining it with product catalog information.
This is where the intellectual value is added. Raw data is often useless. Processed data is an asset. And just like a commercial kitchen needs specific, powerful appliances for different types of jobs, the data world needs versatile processors.
A great analogy.
So our primary processing workhorse and the successor to many older frameworks is cloud data flow. The sources recommend it as the technology of choice when a company is starting fresh, has no existing code or legacy pipelines, and needs maximum flexibility.
Right. Dataflow's greatest selling point is its unified programming model, which is built on the Apache Beam SDK. We spent a lot of time differentiating between batch, the hourly bus, and streaming, the constant conveyor belt. Historically, you needed two separate sets of tools and often two different engineering teams and code bases to manage those two types of processing.
That sounds like a nightmare for maintenance.
It was terrible. Dataflow allows you to define your data transformation logic once and then run that logic on either a massive finite batch of data, like historical archives, or an infinite continuous stream of live data, simply by changing a configuration flag.
So that versatility is why it's ideal for mixed workloads, running those hourly cleanup jobs and live processing data as it comes in.
Precisely.
So if I'm a new company exploring options for both batch and streaming pipelines, Dataflow is the recommended choice because it abstracts away the operational complexity. I don't have to manage servers or scale resources, and I only have to write my core transformation logic once.
Exactly. It lets your engineers focus purely on the transformation logic, the recipe, rather than managing the underlying infrastructure, which is a massive time saver. But this technology is a commitment. It requires using that Beam model.
That leads perfectly into the architectural best practices surrounding data flow, especially regarding unstructured data and the concept of the data lake. If we're ingesting unstructured data raw, log files, emails, sensor output that doesn't have a fixed schema, and we know that data structure might change over time.
Which it always does.
Right. The architecture must allow for reprocessing.
This is perhaps the most fundamental best practice in modern data engineering, and it often involves a hidden cost consideration. If you process data directly as it comes in, transforming it and sending only the result downstream, and you later discover your initial transformation code had a bug,
Oh, no.
or the source data provider changed their format,
Hmm.
You're stuck. You don't have the original raw file anymore to fix the error.
So if the original source system has aged out the data, that data is lost forever, and your historical analysis is permanently flawed. The solution is redundancy and archival safety.
Yes. The correct architectural pattern is to store the raw, retrieved data in a cloud storage bucket first. Cloud storage is cheap, durable, and highly scalable object storage. The perfect archival filing cabinet for raw data.
And then, and only then, you design the processing pipelines like data flow to retrieve the data from that bucket.
Exactly. This practice ensures that if pipeline compatibility issues arise 3 months from now, or if a bug is found in the enrichment logic, you can always go back and reprocess the original raw data. This raw, permanent archive forms the foundation of a well-architected data lake layer.
Okay, so data flow is fantastic for building new unified pipelines. But what if a company is heavily invested in the older, established data processing frameworks? We're talking about massive investments in Apache Spark and Hadoop jobs, which are still staples for large-scale data science and established ETL operations.
Right, you can't just tell them to rewrite decades of code. And that's where Dataproc enters the scene. Dataproc is the specialized service designed to manage, scale, and optimize existing Apache Spark and Hadoop workloads. It's not about writing new code in Beam. It's about migrating and scaling existing code seamlessly.
So the key business advantage here is inertia. If my data science team is used to submitting Spark jobs, Dataproc allows us to leverage that skill set and that existing code base with the least amount of operations work and code change.
It acts like a managed wrapper around the open source cluster environment. It manages the provisioning, scaling, and eventual teardown of the Hadoop Spark clusters automatically.
So if you're a data science team running complex Hadoop jobs in an on-premises data center and you suddenly forecast a massive surge in demand next quarter,
You can use Dataproc to lift and shift those jobs to the cloud without rewriting them. It avoids a costly, multi-year engineering project just to migrate.
and since cost optimization is always crucial, particularly for batch processing where resources might only be needed intermittently, our sources point out a specific technique to minimize cost when migrating those existing jobs.
That technique is using preemptible worker instances when creating the Dataproc cluster. This is an essential cloud finance strategy. Preemptible VMs are spare capacity that Google Cloud sells at a huge discount, often 60% to 90% cheaper.
But there's a catch.
There's a catch. They can be reclaimed or preempted by Google Cloud with short notice if the resources are needed elsewhere.
That sounds incredibly risky for a huge processing job.
It would be, except that frameworks like Hadoop and Spark are inherently fault-tolerant. They're designed to distribute computation across many workers, and if one worker fails, the job automatically reassigns that task.
Ah, okay.
Therefore, using preemptible instances is a perfect way to minimize both infrastructure management effort and operational costs for large batch jobs that can tolerate intermittent interruptions. You save huge amounts of money by using interruptible capacity.
Let's pivot back to the quality problem. We often find that data migrating from unmaintained on-premises systems is messy. It's incomplete, it contains anomalies, we need to clean it before it hits the central warehouse.
Otherwise, we're just building a huge, expensive database of garbage.
Absolutely.
Analysis on dirty data leads to dirty insights, and cleansing is a critical step.
So our sources point toward a specialized preparation tool from Google Cloud for this stage, Cloud Data Prep. How does this fit into the Dataflow Dataproc world?
Data prep is primarily designed for the analysts, not the core engineers. It provides a visual, drag-and-drop interface for data wrangling. When you have messy data, say, files uploaded to cloud storage, the Google recommended practice is this 3-step process.
Okay, what is it?
First, you upload the files into cloud storage, our data lake. Second, you use Cloud Data Prep to visually explore and clean that data.
It allows you to see histograms, profile columns, and identify missing values without writing complex code.
Precisely. It makes it dramatically easier for analysts or non-programming data managers to detect those anomalies, apply consistent transformations, and then export the clean data ready for BigQuery. This separates the exploratory cleaning work from the scheduled, heavy-duty data flow processing.
Preparing the data for the next crucial stage. We've moved the data, cleaned it, and structured it. Now, where does it live? Storage seems simple, but in the world of data analytics, it's defined entirely by the data's purpose.
Yes, and this distinction is paramount. Mixing up these storage technologies is the single biggest architectural mistake a company can make. It leads to huge costs and poor performance.
Okay, let's start with our analytical hero, BigQuery. We must establish clearly that BigQuery is not a traditional database used by an e-commerce site to track inventory. It is a data warehouse.
Right. Let's return to the analogy you mentioned earlier. Think of the difference this way. A traditional operational database is like a cash register. It's optimized for fast, small, concurrent transactions, a tiny lookup to check if product X is in stock, or a quick write to log a single payment.
That's online transaction processing, or OLTP. The cash register has to be fast, reliable, and handle millions of tiny operations every second.
Right. But a data warehouse, like BigQuery, is like a comprehensive library. It's optimized for large, complex lookups and historical analysis. You aren't processing tiny single transactions. You're scanning every book in the library to find a pattern or historical trend across 5 years of data.
That is online analytical processing, or OLAP.
Exactly. That distinction, OLTP versus OLAP, is fundamental. BigQuery is built from the ground up to handle OLAP.
So when should our listener be certain that BigQuery is the right choice?
Well, our source material highlights several specific, non-negotiable use cases.
First, extreme scale. If you are doing marketing analytics and reporting that requires operating on data sets of hundreds of terabytes or even multi-petabytes, BigQuery is the only recommended tool.
A traditional relational database just falls over or costs a fortune to manage at that size. It's designed to parallelize queries across thousands of machines seamlessly.
Second, interface simplicity. If your business analysts are comfortable only with a standard SQL interface, BigQuery is optimized for them. They don't need to learn Python, R, or complex Hadoop syntax. They just write standard SQL.
And BigQuery handles the distribution, complexity, and resource allocation behind the scenes.
And third, mission criticality. When a dataset must serve as the central enterprise data warehouse and must be available 24 hours a day for global business intelligence.
BigQuery, as a fully managed serverless service, fits that bill perfectly. It handles maintenance and scaling automatically.
Okay, so BigQuery handles the analytical power. But what about that high-speed ingestion we talked about? Data coming in so fast that even a standard database can't handle the initial write throughput.
That's the highly specialized domain of Cloud Bigtable. Bigtable is a wide-column, NoSQL storage system specifically engineered for massive write throughput and extremely low latency reads.
And crucially, it is not optimized for those complex SQL joins needed for analysis. It's optimized purely for collecting data at scale.
Exactly. The sources gave a very specific example of its purpose, storing the raw click data of a large portfolio of websites. We're talking about data streamed in at high rates, like 6,000 clicks per minute, or those traffic bursts of up to 8,500 clicks per second.
That volume is staggering.
It is. And it's usually time series data. Bigtable is designed to handle that extreme, constant load much more efficiently than a traditional SQL database or even a warehouse like BigQuery, if you were using it for constant transactional writes.
So it's also the perfect fit for storing high-volume, continuously streaming IoT sensor data.
Ideal for it. Designed to index and handle those endless streams of time-stamped records quickly and reliably.
So we have BigQuery for massive, complex historical lookups and Bigtable for massive, simple, high-speed data collection. It sounds like you really need both in a large system.
In many cases, you do. And finally, we circle back to cloud storage. This is the general-purpose object storage layer, the archival, cheap filing cabinet.
Its primary role, as we established in the processing section, is acting as the ideal location for the raw, unstructured data lake, ensuring that we retain the original source data for reprocessing purposes. It's the ultimate backup and source of truth.
Absolutely. And while it is incredibly cost-effective and durable, it's important for you to remember that data stored here is not optimized for ease of analysis compared to BigQuery.
Right. Analyzing flat files directly usually requires external specialized processing engines like Dataproc, and performance is slow for ad hoc exploratory queries. It's the cheap archival layer, not the end-user analysis platform.
Precisely.
Okay, we've ingested, processed, and stored the clean data in BigQuery. Now we move to analysis. When you're dealing with petabytes of data, simply running a SQL query isn't enough. If you query inefficiently, you risk running up massive bills and waiting hours for results.
Oh yeah, we have to optimize. And optimization in BigQuery usually boils down to one goal: minimizing the amount of data the system has to scan to answer your query.
Because BigQuery is often paper query based on bytes scanned, so efficient query structure means dramatic cost savings.
Huge cost savings.
Let's tackle a truly massive problem: analyzing 10 petabytes of historical user data. We know that a specific column, say userid, is frequently used as a filter in our daily reports. How do we structure that enormous table to minimize both cost and improve performance for queries filtering by userid?
This requires using the dynamic duo of BigQuery techniques, partitioning and clustering. Think of partitioning first. Partitioning splits the giant table into separate, manageable segments based on a date or time field. So if your query is only looking at data from October 2023, BigQuery can instantly ignore 99% of the table.
That makes sense. We eliminate data based on time. But what if I need to find the data for userid 1234 within that October 2023 partition? It's still a huge chunk of data.
That's where clustering comes in. Clustering organizes the data within those partitions based on the chosen column, like userid. When the data is clustered, it's physically grouped together on disk. So when a query filters by userid, BigQuery doesn't have to scan the whole October partition.
You can just jump directly to the small block of data where that specific user's records reside?
Exactly. So the recommended structure for this massive 10 PB scenario is to partition by date and cluster by that frequently filtered column, userid.
The date partition gives you the macro filter, and the clustering gives you the micro filter.
And that synergy radically reduces the byte scanned, improving query performance from hours to seconds and cutting costs exponentially. It's the difference between looking for a letter in a giant filing cabinet versus looking for a letter in a specific, clearly labeled drawer within that cabinet.
That's performance optimization. Now, let's talk cost optimization and data retention. Say we're writing application logs to BigQuery, and company policy dictates that any logs older than 45 days must be removed to optimize storage costs. Running manual deletion scripts every day sounds tedious and prone to error.
Right. You should never manage data retention manually in a system like this.
No. The best practice for managing time-based data retention in BigQuery is to use the native feature built around partitioning. Make the tables time-partitioned and configure the partition expiration at 45 days.
So once a date partition turns 46 days old, BigQuery automatically and cleanly deletes the entire partition without running any compute-heavy query or requiring any operational oversight.
That's pure cost efficiency and compliance rolled into one.
Now let's look at a dilemma we set up earlier. We have high-speed IoT sensor data stored in Cloud Bigtable, but the data science team needs to run complex aggregations and ad hoc standard SQL queries on it for their monthly reports. They don't need real-time access, but they need the full power of BigQuery's SQL engine.
Okay, so you have two bad options and one excellent solution here. The bad options are, first, rewriting all your complex analytical SQL into a Bigtable-friendly format, which is difficult and limiting. Or second, migrating or copying all 10 petabytes of IoT data out of Bigtable and into BigQuery every single month.
Which is costly, slow, and operationally painful.
So we need to connect the power of BigQuery's SQL engine to the source data in Bigtable without physically moving it.
And that's the excellent solution. The most efficient architectural pattern is to use BigQuery to query the data directly in Bigtable using external data sources, which is commonly known as Federated Queries.
Wait, so BigQuery can run a standard SQL query, but the data is physically sitting somewhere else in Bigtable. How does that even work?
BigQuery essentially acts as the analytical command center. When you execute the query, BigQuery sends the request to Bigtable, Bigtable returns the necessary subsets of data, and then BigQuery executes the complex SQL processing that joins the aggregations using its powerful engine.
This sounds like a huge cost and time saver. It means we don't need to double store the data or pay the high processing cost of constantly copying massive data sets just to run a monthly report.
Exactly. You leverage Bigtable's efficiency for ingestion and BigQuery's power for analysis. It's the best of both worlds.
Okay, once the data is clean, stored, optimized, and analyzed, we reach the final stage, display. This is where the output becomes useful to humans, dashboards, reports, and visualizations that drive decisions.
We need a tool built for business intelligence, or BI. The recommended modern BI platform in our sources is Looker. But what sets Looker apart from other visualization tools? There are a lot of them.
There are, and it's specifically highlighted because it includes a crucial component called a semantic modeling layer, known as LookML. Why is this architectural layer so important to the integrity of the data ecosystem?
It solves the chaos of inconsistent metrics. In large organizations, different analysts often define the same key metrics, like customer lifetime value or monthly active users, in subtly different ways across different departments.
Right, so Analyst A defines MAU as a login in the last 30 days. but analyst B defines it as an action in the last 30 days.
And both dashboards will show different conflicting numbers.
The resulting business decisions will be based on incompatible realities. It's a huge problem.
Massive one. LookML solves this by allowing metrics and business rules to be defined once in a central, consistent model, and then used uniformly across all dashboards, reports, and exploratory queries. Because LookML sits as the single source of truth between the raw BigQuery data and the visualization layer, it ensures that everyone in the organization is looking at the exact same data, defined by the same rules.
It enforces consistency across the entire enterprise.
That's its whole purpose.
We've built a brilliant, fast, and powerful architecture that spans from click to chart, but none of that architecture functions or survives an audit without robust rules for access, security, and cost control. This is the crucial topic of governance.
And this is where complexity often spikes dramatically. Governance is about control and risk mitigation. It's who can see what, who pays for what, and how we ensure compliance with increasingly strict global regulations around sensitive data.
Let's start with cost control in BigQuery, which operates on a pay-per-use basis. If you're running a massive analytics platform, you need to monitor queries in real time to discover the most costly queries and which users are spending the most money. Simply waiting for the monthly bill is too late.
It is. Relying on the standard billing report doesn't give you the necessary granular detail. It's aggregated and delayed. To monitor usage in real time, you have to look at the job execution logs, which contain details like data scanned, user ID, and compute time.
So what's the solution?
The recommended solution is beautifully architectural. Create a cloud logging sink to export BigQuery data access logs to BigQuery itself.
You're turning the audit trail of the data warehouse into another table in the data warehouse.
Exactly. You are treating your own usage logs as data, importing them back into a dedicated BigQuery auditing table. You can then query that new generated table instantly to extract job information, who ran the query, how much data was scanned, and therefore the cost incurred.
It's using the power of the COOL to audit itself in real time.
You got it.
And what about basic historical audit purposes? Say, a security team needs to see how many queries each user ran in the last month.
For standard audit visibility, who did what and when, you rely on the built-in system, cloud audit logging. You simply view the audit logs and create a filter on the query operation to gather the necessary historical usage data. You don't need the complexity of the logging sync unless you need that deep, real-time cost analysis.
Access control is one of the biggest headaches in large organizations. Let's tackle the complex scenario where data is distributed over several Google Cloud projects. Perhaps different departments own their source data in separate projects. But all query costs must be billed on a single separate project.
Yeah, often a central finance project. Furthermore, users must be able to query so they can run jobs, but not edit the data.
Okay, this scenario is all about separating the responsibility of running the computational job and thus paying for it from the ownership of the data.
Which requires a precise combination of two specific IAM roles on two specific projects.
Right. The correct configuration requires granting the users the role of BigQuery job user on the billing project and the role of BigQuery data viewer on the projects that contain the data.
Well, let's break that down. The job user role allows the user to initiate the computational task, the query. Because we grant this role on the designated billing project, that project's budget pays for the computation.
Okay.
The data viewer role gives them read-only access to the tables they need in the data owner's projects, ensuring they can see the source data, but cannot accidentally or maliciously edit it.
It's a precise application of granular access and cost separation.
It is.
Wow, that's a great example of using roles to manage both cost centers and data integrity simultaneously. Now let's talk about data granularity. If web traffic data is split into separate data sets by country, and analysts from each country should only see their respective data, how do we efficiently manage that specific subset access without creating hundreds of roles?
We use a combination of IAM for capability and BigQuery's native dataset sharing for visibility. The best practice is to first define security groups per country. So, for example, Analyst Group France. We grant the overarching group, say, all analysts, the general IAM role of BigQuery job user on the central project so they have the power to run queries. Then we use the granular BigQuery feature to share the appropriate dataset with view access with each respective country group.
So the IAM role gives them the engine to drive the query, but the sharing mechanism on the dataset itself acts like the key, determining which car they are allowed to drive.
That's a perfect way to put it.
Finally, we must address compliance and security regarding personal identifiable information, or PII, and sensitive health data.
Mm.
When legislation requires the deletion of health data upon request, say, for members aged 8 to 30, how do you handle that in a massive multi-petabyte data warehouse like BigQuery?
Since BigQuery is fundamentally designed for analysis and supports standard SQL operations, the most compliant and simple solution is to ensure your data is tagged with a unique identifier. Upon a deletion request, the best practice is to use a unique identifier for each individual, and upon request, execute a standard delete statement to remove all rows from BigQuery associated with that identifier.
And BigQuery just handles the physical deletion in the background.
Right, it offers the simplest path for compliance.
Now, what if you don't need to delete the data, but you need to restrict access to only the PII columns? For example, the compliance team needs PII columns, but the data science team needs the rest of the table for modeling without seeing any sensitive names or addresses.
Right, you need to mask the data without duplicating the storage. Copying the table is inefficient and risky. The best practice here is to use views to mask the PII.
How does that work?
The steps are explicit. Create a new dataset for the data science team, create views of the source tables excluding the PII columns, and then crucially authorize that new view to access the original source dataset.
So the data science team queries the view, which looks exactly like a table, but securely filters out the sensitive columns. The data stays in one place, storage costs are minimized, and the view acts as a secure, compliant filter.
That is an elegant solution. Now, moving to high-level encryption. If a company has extremely strict security requirements and needs to generate and retain control of their encryption keys outside of Google Cloud,
We enter the realm of customer-supplied encryption keys.
exactly. This requires using the centralized key management system, Cloud KMS. The required procedure is to first import a key in Cloud KMS, thereby giving Google Cloud access to use the key but not own it. Then you create a dataset in BigQuery using the customer-supplied key option and select the created key.
This ensures the company retains control over the key used to encrypt the entire BigQuery dataset, meeting that external governance requirement. Finally, let's address the threat of data exfiltration malicious insiders, or compromised code trying to tunnel massive amounts of data out to a bad actor when connected via a VPN. Standard firewall rules aren't enough to secure access to massive cloud resources like BigQuery and cloud storage.
Not at this scale. The ultimate high-security guardrail against data exfiltration in this hybrid architecture is to enforce a perimeter. Configure VPC Service Controls and configure private Google access.
I need an analogy for VPC Service Controls because that sounds like pure engineering complexity.
Think of it like this. VPC Service Controls create an impenetrable electric fence around your cloud resources, BigQuery, cloud storage, everything. Even if a malicious insider compromises an account or an application server inside your network perimeter and they manage to get valid credentials, the controls prevent that data from physically leaving your pre-approved network boundary. They can't export it to a Google Drive account outside your project or upload it to an external storage bucket.
That prevents the data from leaving the playground regardless of who has the keys.
Precisely. And when you combine that with private Google access, which ensures traffic between your on-premises network and Google services stays on Google's private, highly secured network rather than traversing the public internet, you achieve the highest level of data protection against unauthorized data movement and insider threats.
It is the final layer of governance complexity, but the most important one for security.
Without a doubt.
That is a masterclass in locking down the entire data ecosystem. We've covered everything from the first click event to the final audit log. Okay, let's recap this massive architectural journey. We started with the fundamental separation of the raw flow, distinguishing the continuous streaming data, the conveyor belt, from the bundled batch data, the hourly bus.
Right. We then followed the data through the 5 critical stages of its life. We saw ingestion driven by PubSub acting as the essential elastic decoupling layer to handle those unpredictable traffic spikes of 8,500 clicks per second.
And specialized tools like DataStream for real-time changed data capture from legacy databases.
Then we moved into processing with Dataflow, our versatile, unified engine for new, mixed workloads, contrasted with Dataproc for efficiently scaling existing, fault-tolerant Spark Hadoop jobs.
And we learned the importance of leveraging cost-saving, preemptible instances and, critically, storing the raw data in a cloud storage bucket first to enable future reprocessing.
Then came storage, where we made that vital distinction between the high-speed, high-throughput collection point cloud Bigtable optimized for IoT and clickstreams, and the ultimate analytical powerhouse, BigQuery, designed for multi-petabyte OLAP analysis using standard SQL.
And finally, we covered analysis and display using performance techniques like partitioning and clustering in BigQuery to dramatically cut costs and latency, leveraging federated queries to analyze data residing in Bigtable without moving it.
And enforcing metric integrity through Looker and its semantic layer, LookML.
It's all connected.
What's fascinating here is that while we focus on the physical architecture, the pipes and the servers, the true ongoing challenge is governance. We spent significant time discussing how the system must be governed, ensuring PII masking, using authorized views, separating billing and access roles across multiple projects using IAM.
And preventing data exfiltration using the ultimate perimeter lock, VPC Service Controls.
It's the rules you place on the system that determine whether the architecture is secure, compliant, and fiscally responsible.
It's clear that building a data system isn't about picking the coolest tool. It's about matching the right tool streaming versus batch, warehouse versus high-speed storage, to the specific stage and purpose of the data, and then locking it all down.
And this raises an important question for you, the learner, to consider as you digest this massive flow of information. Now that you know how the data moves and the purpose of each specialized tool, how would you start designing a data archiving system purely optimized for maximum cost efficiency?
So forget real-time performance.
Forget it. Assume the goal is only weekly reporting. How would you use the cheapest possible combination of storage Bigtable versus BigQuery versus cloud storage and processing preemptible versus standard data flow instances to minimize the weekly operations expenditure?
Something to mull over as you begin mapping out your own data architecture. Thank you for joining us on this deep dive into decoding data analytics, and we look forward to continuing your learning journey next time.